Hey everyone, welcome to Technical Ecology, and I am Kalpapran. I am a biodiversity conservation student at Nottingham Trent University. In this channel, we talk about the technicalities, concepts, and theories of ecological conservation. And if that sounds interesting to you, welcome. So, this is the second episode of the R series, and today we are going to talk about how to create vectors and use vectors for doing basic arithmetic calculations. We're also going to learn about how to do basic arithmetic calculations without using vectors and all those different exciting stuff. So without much further ado, let's get into it. Okay, let's get into it. So let's just open up our studio. There we go. I will just restart R just in case things are from the scratch. Okay. Right, let's get into R. Okay, first thing first, like we discussed in the earlier episode, it's much more helpful if you have one working directory where you have all your files, all your objects. Later towards the end of this series, we are going to talk about how to create our projects so that you can have multiple files of a single project in one kind of a workspace. All right, with that being said, let's first have our working directory set up. It's the same thing as you can see, project YouTube, R scripts, but this is episode 2, so it goes under episode 2. Now, after setting the working directory, what I want you to do is probably have a look at the global environment, have a look at the plots, or let's say the files that you have, the plots or the packages that you have already loaded, because sometimes there are unusual or unwanted objects in the global environment which kind of messes up the code and it might mess up your entire calculations. That's usually not the case unless you save your workspace, but it's a good practice to not save your workspace, but even if you do, you have a different folder which stores it, and whenever you open R, it'll make sure that it's a completely empty canvas. Okay. So what today first we're going to do is we're going to talk about the basic arithmetic functions that can be done in R. Well, you can use R as a basic calculator, which we are going to do for now, and then later dive deeper into, you can see the log, we'll talk about the Euler's number, and we'll talk about different sorts of functions in R. So R comes with the base arithmetic functions like product, which is the multiplication, or sum, which calculates the sum of the objects, or sqrt, which creates a square root. So let's get into it. Well, first of all, R uses this format called PEMDAS, PEMDAS, which kind of sounds funny, but that basically means that when you have a set of operations in R, let's say you have multiplication, you have addition, you have subtraction, so then R runs these operations in a very chronological manner according to PEMDAS. So PEMDAS basically stands for P is for parentheses, E is for exponent, M multiplication, D division, A addition, and S is subtraction. So PEMDAS is not an actual word, it's just an abbreviation that helps me keep it in my mind. Also, I think I picked it up from an R book that I actually started out when I was learning R. And the basic arithmetic functions are plus, minus, multiplication, / is the division, and this is the modulus. P, which stands for parentheses, basically means that it will do the operations that's inside the parentheses first, and after that it goes to exponent, and then it goes to division, then addition, multiplication, division, addition, and then subtraction. So let's just do this line of code first. So we want to know the result of 14 divided by 6 plus 5. So in a normal sense, it will first execute this part of the code, which is 6 plus 5, and then it will divide 14 by 6 plus 5. So if we just run this code, we can see that we get the value here which is 1.272727. Okay, Now there are also functions in R which can calculate the square root or root of any value. So one of and for getting the square root, we just always use the function called sqrt. It's much more simpler. So if we run the square root of 4, which is 2, so we'll get 2, and if we run the square root of 79, we'll get 8.79. Now bear in mind that negative numbers doesn't have its square root, which it gives you an infinite value, so it'll probably throw up an error. So I'll just try that out. sqrt, let's say minus 67. Yeah, see, it is an infinite value, so it throws up an error showing an nan was produced, which is basically infinity. If we, again for an example, if we use this line of calculations, first what it will do is it will find the exponent of 7 to the power of 2. Then it will find the multiplicative, like PEM plus PEM, so multiplication between 3 and 69. And then it will divide whatever the multiplication value is with 9 minus 3. And whatever the value of 3 into 69 divided by 9 minus 3 is, will be added to 7 to the power 2. So if we just run this code, we can see that it's 69. Okay, now what we are going to talk about is log transformation. Basically, log transformation is used to reduce the heteroscedance. I always I will struggle with this word. Heteroscedasticity of linear regressions or any sort of regression function. So what this term means is that it decreases the fluctuation, the variance, the fluctuation of the variance in relation to the independent variable. So if we say, let's say if we have a graph where we draw the line of best fit, but the variance is much fluctuating. Like, let's say if the independent variable increases, the variance, which is the distance of the points from the line of best fit, it might either increase or decrease, or be very fluctuating, like it might increase and then decrease. So just to decrease that, we use log transformations, which I will delve into later in the more in detailed and in-depth videos about how to create let's say distribution models, or how to create a model that can find a relation between independent environmental variables and, let's say, species distribution or species population density. So all sort of those fancy stuff. So basically, the less is the variance, the more better the model is to explain a certain response variable. And then again, it's very highly valuable in statistical analysis. Log transformation can also approximate normal distribution. What I mean by this is that mostly in ecological sectors, when you get data, the data might not seem normal. Like in most cases, if you, let's say, calculate the percentage of anurans from from the edge of a forest to the interior of a forest, you'll find that the edge effect kind of increases the annuran. It's not always the case, but in most cases, the edge effect kind of increases the annuran diversity, and then towards the forest, it kind of as we are approaching the middle of the forest, it kind of decreases, but then again in the inside the interior, it kind of increases. It might seem like a curve that goes down and then gradually goes up, but if we take the larger context, we are just doing it for a smaller area, so we are getting it looks like that the distribution is not normal, or let's say the abundance is not normal, abundance in particular region. So now if we do the same for multiple points and then kind of clump up all those data, we'll see that it's kind of a normal curve. It'll go up eventually, and then it'll have a highest peak, and then it'll come down. Now this is not very evident in ecological data that you collect. So we can again use log transformation to kind of convert the data that we have and make it assume a normal distribution, approximated normal distribution. Assume is not the proper word here. Also, it is helpful in handling outliers. So outliers can skew your data. So if you again have a normal distribution, it kind of standardizes the data, I would say. Right. So that's about why we use log. Now I'll just give you an example of using the log function. The log function basically you call the function log, and then in parentheses you have your variable that you want to find the log of. You can either do this where, like, I'm just showing it for practice here, that x equals to 100, but even if you just x equals to 1000, but even if you just remove x, it will still run. However, it's a good practice if you are just starting out to learn that the main variable that the function is going to act on is written as x, or at least R identifies it as x. Like x is the first argument of the function. So log of 1000, and base is basically what's the base that you give for the log function. Like it can be 5, it can be 4. So if we run the log of 1000 to the base of 10, we get it's 3. So 10 to the power 3 is 1000. So that's what basically log is. Now I want to also talk about this Euler's number, which is 2.718. So we have something called natural log. So basically when we do log transformations, the natural log is basically a log function raised to the Euler's number, which is 2.718. This is very conventionally written as e. Like Euler's number is written as e, and whenever you work with R, you'll see later that e shows up. E is basically Euler's number, so e to the power something is basically 2.718 to the power something, let's say n. Log cannot be negative. Like you can't find the log of a negative number, whereas natural log comes into play here, especially as Euler's number can be negative, which is unlike log. Also, Euler's number is basically the inverse of the natural log. Like 1 by natural log is basically the Euler's number. When you don't specify a base, it basically computes the natural log, which is to the Euler's number. So log of 10,000 to the base of e, and not base of 10. So if you see the exponent of 8, which is Euler's number to the power 8, will give you 2.718 to the power of 8, which is 2980. This is something called, now I want to come into something called the E notation. E notation is only done by R so that it is much more easy to read through. Like it eases the readability of your results. So if you just run this, so what R will basically do is it will show the same number, but it will crop the number or trim the number to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Yeah, it will show you 7. It will show you 7 digits of the massive number that you have provided, and then it will show E plus 13, which basically means 2.857389 E is into 10 to the power of 13. So you can see that if we do this, if we multiply this value, just this portion of it, to 10 to the power 13, we will get this value. Now, just because it trims off a few digits from 9 onwards, that doesn't mean that R deletes it. It's still there. It's just not visible to you. So even if you do any kind of computation, it will still take these digits into account. It won't decrease the accuracy of the calculations. Okay, now we'll come to something called assigning objects. Assigning objects is basically assigning variables, but see, all variables are objects, but all objects are not variables. So by that what I mean is that I'll delve into something called vectors later. So vectors are basically objects which can store multiple values, whereas variables or objects x and y here can store just one value. So if I like here I've written the code x less than minus 589, which basically does is that it creates a variable called x and it gives it the value of 589. You can see when I do that, and if I print x, it will return 589. Now there are two ways of assigning values to a variable or an object, is by this method and also is by something called equals. So you can do the same thing, x equals 589. So if you do that, if I run this, it will basically have 5, and just for ease I'll just change the number so that you can see that it overwrites x. So if I just run this, you can see 587, and now if I print x, 578. However, I kind of prefer using this method because it's not so confusing when your code runs long, especially because when your code runs long, you'll use equals maybe to compare one variable to another. Then we use equals, something like here where you assign the object. It's a good convention. Like you can't use less than minus to this, it'll just throw up an error. No, it didn't throw up an error, I didn't know that. Something new for me. For me, I like to adhere to less than dash for assigning values to any kind of objects or variables, because it's much more convenient to read through the code later. Because if you use equals in all the cases here, and then you use equals for calculation as well, it might cause a lot of confusion, especially if your code is very long and it's very complex. So it's just a personal preference. You can do U and you can just go ahead with equal, especially if you're coming from something called like Java or C++, where equal is used, or even Python for that matter. All right, so after assigning the variables, their values x and y, R basically uses x and y as objects which can be worked on. Like what this code means is that we create an object called result, which stores the value of x into y. So what R will do is R will print the value of x, which is 589, and then it will multiply print the value of y 394, and then it will multiply 589 by 394. So when you have objects, you can kind of play around with different variables. Now, like it doesn't seem intuitive now to just why to even assign 589 to x. Why just not type it down? Like I'll come back to this later, because you can see here that if I just run this and then run result, you get the value here. What if you want to multiply, let's say 78 with the results that you get here? You can do it here individually, but then again, if the code runs long, if the operation is much more complex, let's say the results again be used in another function or another arithmetic operation, then you can just use the result object in those operations, instead of just again multiplying 589 by 394. It just becomes way more convenient in the long run. So if I again print results, you can see that it overrides the results that we found earlier to the sorry, it's not results, there we go. There you can see that it overrides the older value that it computed. All these, like I told, are objects. Now if you want to see all the objects, you can just see here in the global environment in this panel. But but if you are using the base R version, then you can just run this function called ls, which will show you all your objects that you have created. Now you have to stay consistent with equals and this, because it's a good convention, and in the long run it's a good practice to be consistent with whatever you use. If you use equals, then just use equal, don't use less than dash. All right, now we come to something called vectors, where it kind of starts getting way more interesting. Like everything before it was quite bland. Like for me it's bland. I don't want to go on a rant about some things being bland, but the basics are really important. All these are really important, especially if you are if you directly jump into something called vectors, then you might face a bit of confusion. Like always get the basics. Like I have learned it in a very harsh way, that you need to know the basics to actually be able to make sense of more complex things. It is very tempting to just jump into the main thing and disregard the basics. Even something like photography. Like I started out photography by clicking a few photos of flowers, and then I directly jumped into wildlife, where I really struggled in the beginning, because things like if you don't know how to use the shutter speed at what time. Like when a bird flies, you're not using a very slow shutter speed. You can't afford a 1/5 shutter speed when the bird is flying at a very high speed. You need a very like 1/250, 1/500 at least, according to your lens again, lens and light and everything. Okay, I don't want to dive much into camera, but yeah, you need to, what the basic point I want you to drive home is that you need to know the basics. All right, so now let's dive into vectors. Vectors are again objects which can store a large set of values. So you can see here that I have created an object called vec, and here I have stored all the values that I want. Now C, what basically means is concatenate. Concatenate, I think it's concatenate. Yep, it's concatenate. So R basically concatenates these values that you have provided, like C, which basically means concatenate, and then in those parentheses you input all the variables into it. Now when you do this, it creates a vector, and if I print this vec, you can see that it creates a vector which has these values in it. And when it has these values in it, what R also does is, you can't see it here, but it indexes each value. So 1 is assigned the index of 1, 9 is assigned the index of 2, 6, 3, 68, 4, then whatever it says, and so on, 4, 5, 6, 7, 8, 9, 10. It always starts with 1, it doesn't start with 0. Vectors can be, it can even be variables. So let's say the result that we had found earlier can also be inputted in as a vector. So if I create something called the new vec, which basically contains the vector that we created earlier, the results, and x is this value. So if I run this and then I run new vec, you can see that it prints all the results. So we can see vec is basically 19668, which it prints it there, and then we have the results, which is this one, and then we have our value of x, 589. Now after knowing this, we can dive into something called sequence repetition, sorting, and links. So sequences are very useful if you want to just have a sequence of numbers, probably, or maybe you want a sequence of even numbers, or maybe you want a sequence of numbers between 1 and 2, if you're going to the float variables like 1.2, or if you want, let's say, 10 variables, 10 values between 1 and 5. So then something like sequence comes into hand, and is mostly used for when you're creating for loops, which we will delve into maybe the 4th or 5th episode, or when even plotting data points for that matter. So to basically illustrate how we create a set of sequence of values is by using the colon, not the semicolon, but the colon. So if I print 5:67, it will create a sequence starting from 5 and ending to 67 by the increment of 1. So if I just do that, you can see 5, 6, 7, 8, 9, 10 to 67. Now we can also again use objects or variables for that matter, like ht will store 78, and then gf is another variable that we create, which stores the sequence from ht, which is 78, to -34 plus 5.7, which basically means that -34 is like 78 is the first, like from, so I would just say from the first value, and then it will go all the way down to -34 plus 5.7, which is, let's just calculate, -34 plus 5.7, so -28.3. So it will calculate all the numbers from 78 to -28.3. We can see here, even though we have given point to it, it still does it like in 1 plus or -1 increments. It doesn't go into points. So To do that, like to change the increments, we can use something called by, the by at argument of the sequence seq function. So if we want the sequence from 67 to 76 by an increment of 4, so we just use by. So 67, 71, 75. So so you can see that when I ran this, the final value just stops at 75. That's because our final value that we want is 76. So if it goes again an increment of 4, it won't be a sequence from 67 till 76. It will just add it'll go to 77, 75, 76, 79. So it'll go to 79, which is again more than 76, which we don't want to. Okay, sequence, we'll see another example where we want a sequence from 67 to 76, but now length.out equals to 56 means that we want 56 values to be shown in total between 67 and 76. Now R will compute what will be the increments between them or decrements. So if I just run this, you can see that there are 50, 51, 52, 51, 52, 53, 54, 55, 56. So we have 56 values. R just created a sequence of 56 values between 67 and 76. Now if we go to this line of code, we want a sequence from 76 to 67. Now you can see that I have kind of inverted it. So we want it in a decreasing manner. And to do that, we can always just use the -4. So if you run this code once, the initial one, you can see that it's 67, 71, 75. Now it should basically be, it should basically be 76, 72 and 68. So it subtracts -4 from 76 until it reaches 67, or at least something less than 67, which in our case, which in our case is 68. Okay, so from this point onwards, I haven't written much code because I'll be doing it real time so that you can just work along with me. I hope you got a basic idea of creating objects, vectors, but there are certain things that is just coming to my mind now, and I want to kind of go through in real time. Okay, so what we are going to talk about now is basically repetitions. So repetitions is basically if you want one value to be repeated more than once in a sequence or in a vector, which sequence doesn't do it by itself. So let's say we want to get a repetition, we basically use the rep function, and what we want is x equals 1, the value of 1, to create a vector to be repeated, let's say times equals 5. So it will create a vector. It won't create a vector because I haven't assigned it to anything, but I'll just assign it to, let's say, dy. So it will create a vector dy, which basically prints 1 5 times. So now if we just print dy, we can see that 1 1 1 1 1, which is 5 times. So rep function helps you to repeat value in a vector, and times is the argument that you use for mentioning the number of times you want. Now we can also have something like, let's say, rep x equals, we want to concatenate something like 2, there we go, and we want this part, we want this we want this part of the code C 2 5 6 7, which is stored all together, to be repeated, let's say 7 times. So if I just run this, you can see 2 5 6 7 2 5 6 7 2 5 6 7, which is being repeated 7 times. So after this, there is another way of printing repetitions of concatenations. Let's say we have the same numbers 2 5 6 and 7, but what we want now is to repeat each of these values inside the concatenation 2 5 6 and 7. We want each of them to be printed, let's say, 3 times. So if I run this, you can see that 2 is printed 3 times, 5 is printed 3 times, 6 7. Now what we can do is we can create a concatenation of repetitions as well as sequences. So let's say we want to create a concatenation of, let's say 3, 8, and let's say 4.5, and then we want a repetition. Let's say if we want the repetition of, let's say, a value of 5, and each value to be printed 4 times, and the number of times will be a variable, let's say a variable foo. So if we give a value of foo as a value of 6, so foo is basically 6 times. And we can also in this concatenation have a sequence, let's for that matter. So if we have a sequence from 2 to let's say 1, and we want the length dot out to be, let's say, foo, again this one, then we add just +1. So if we run this, unexpected symbol, sorry, there should be a comma, and there we go. So 5 times, and then we have the sequence, which is from 2 to 1, and then length will be foo +1, which is 6. So these are the values. Now another point I want to come to is called, again, sorting. So sorting is done using the function called sort, and it is, sometimes we might want something to be sorted in an increasing manner or decreasing manner. So regardless of what our needs are, we always use the sort function. Let's just see an example. Let's say we have a value of a concatenation of values of, let's say, 2.5 minus 5, 6.9, yeah, 8.9, and then there we have an attribute called decreasing. Now if you give decreasing equals to true, what basically happens is that it prints the highest value and then it goes in a decreasing manner. So 8, what's the next lower value? It's basically in a decreasing manner. Now if we do the same code, but if we have decreasing as false, then what happens? It is an increasing manner. It's not in a decreasing manner. So -5 is the lowest, 2.5, and then 8.9. And decreasing is again a logical value, which is either true or false. So it is way more helpful in things like running a for loop. But I'll come to logical vectors later with specific examples. That's basically the sorting function. Now we can also have sort sequences using the sort function. So for them, let's say we create a value, a vector of sequence from 4.3 to I'm sorry, not 4, just 4.3 to let's say 5.5, yeah, and then we want ln gth1 equals to, let's say, 6. All right, so if we just print foo, so we can see we have 6 values from 4.3 to 5.5. Here what we want to do is we want to sort it, let's say, in a decreasing manner. So the highest value goes first. Instead of 4.3, 5.5 will be there, and 5.26. So if we just use the sort function and then we call, like, for x here, the variable will be foo. You can also do just sort and then foo, and then we have decreasing equals to, let's say, true. So you can see here, it just turns the sequence around. So it's the highest value and then the lowest value. We can also have this sort function to be stored in a different variable. So let's create a variable called bar. So if we store it here, then if we just print bar, you can see that stores a value. It's like this is a very just printing this one is temporary, so it isn't stored. But if you want to work with, let's say, this sequence foo, and then we want to work with bar at the same time, then we just use that. We can also sort foo and bar, like these two together. By what together I mean is that, let's say we print the sort function and then we concatenate foo and bar. Yeah, so we concatenate that, which is basically the value for x. So x is this, and then decreasing equals to false. Yeah, when we run this line of code, sort x equals to foo and bar, so it basically creates a new concatenation of values which contains the values from foo and the values from bar, and it sorts it in a decreasing manner. So highest value to the lowest value. It's a downward slope. So now we have kind of sorted out sorting, repetition, and sequences. What I want to delve into next is something called length. Length is basically the number of values that's present in a vector. So to get the length of a vector, we just use the it's very intuitive, the length function. So what we do is, let's say we have a concatenation of, let's say 3, 6, 5. Okay, we have this concatenation. Now we can count it. We can see that there are 5 values in this concatenation. Now if I just run this, it gives 5. It's very well, like you'll be asking me why are we even using this? It's so intuitive, right? You can just read through it and then find it. Now it's easier now, but when we have data, which we will talk about later, when we have data that is like, let's say, thousands of that has thousands of values, so a vector might contain thousands of values. Now you can't individually go and count each and every one of them, so you can just use the length function. Another let's give another example. We have length length x equals, we need values from, let's say, 56 to 98, and we don't know, like here we don't know what are the number of values. We can count, we can think, but we can say, if you just run this code, sorry, we don't need to see here. If you just run this code, we can see that there are 43 values starting from 56 until 98. Okay, now what if we want to find the length of multiple vectors? So let's take the example of this one. What are the number of values present in this vector? So let's assign that to a certain variable first, u. Okay, now we just run it. Sorry, there we go. Oh, okay, sorry. Yeah, so the foo variable was replaced later in the code. Like I had created a vector, so you can't have a vector as a times attribute, times argument, sorry. So now if I run it, u stores these vectors, and now what I want to know is the length of this entire vector. So again, call the length function, length, and then u. Now if I run this, you can see that there are 34 values in this vector. You can go ahead and individually count it to verify it, but yeah, that's it. Actually, let's just do it. Let's just print u. See, 31, this is 31, 32, 33, 34 values. All right, so now what I want to talk about is subsetting and indexing. So what I mean by that is, like I've spoken about index, right? So every value in a vector has its own position, own index. Like I spoke earlier, in this vector C365 3 6 4 5 7, 3 is 1, 6 is 2, 4 has 3, I mean the index, I'm talking about the index. 5 as 4 and 7 as 1. 7 as 5. Indexing is really helpful when we want to subset variables, but just for now I want to show you how we can extract that extract a value from a vector using its index. So let's say I create a vector called myvec, which basically contains 5. I'm just putting in random there we go, random values. Now what if we want to, first let's find out the length of my vec. Okay, did I run this? Okay, is 16, right? Now 16 is the index of this number, and 1 is the index of the first value. Now if I want to extract the first value, so what we do is index it. So basically to index a vector, we just call the name of the vector first that we have stored the object as. So myvec, and then in square brackets, not parentheses but square brackets, we just put the index value. Now if I just return this, you can see it's 5. And if I do the same thing, and since the length is 16, if I type 16, we can see 43 is shown. Now again, if you want, let's say the fifth value, so the fifth index, so it will return 5, which is 1 2 3 4 5. Yeah, 5. What we also can do, we can assign indexes to a certain variable and then use that variable to find the last second or last third value from vector. What I mean by that is, let's say for example we create a variable called myvec.len, which is basically length. So first we calculate the length of myvec. So myvec length basically stores the value for the length, which is, in our case, myvec is 16. Myvec length, which is 16, right? Now if we want to extract the last second value from this vector, so what we basically do is we go to myvec, yeah, and then in square brackets we have myvec length minus, which is 16, minus 1, which is the last value, minus 1, which is the last second value, which gives us 3, which is the case here. We can see. Now if you want the last third value, minus 2, which is 4. So it is useful again when you have thousands of values in a vector. This is what I basically wanted to show for how to use length in coordination with indexes. Now I want you to also keep in mind that when you extract the index of a variable of a vector, it is always stored in an arithmetic form, so you can perform calculations on it, or at least you can use it in other functions as a arithmetic value. What I mean by that, let me just give you an example. Now we know that myvec.length basically contains the length of myvec, our vector, and I want a sequence from, let's say, 1 till myvec. Now since myvec is an arithmetically computable value, myvec.length, what it will do is it will run a sequence from 1 till 16. 16 is the value, right? Now what if you want to, let's say, subtract a value from this vector? From myvec you want to subtract the value. Then again indexing comes into play. So what you do is you have my vec. It's my vec, and then you just add a minus and the index number. So if you want to remove the first element, which is 5, from the vector my vec, we use just -1, which will return the variable of my vec as 3241. Like you can see that 5 is gone, because if I print I haven't stored my vec to anything. My vec, if you can see it's 5.3 from my vec, and my vec -1, which is the first index, 5 is gone. So you can see it here. Similarly, what you can do is you can store this in a different object, which creates a different vector altogether. So if we create a vector called baz, and then we have this, and then we print baz, we can see that it basically does the same thing that was done earlier, but now it's subtracted the second element from my vec. Like my vec, the second element 3 is gone from this place. Now we can, again, what we can do is if we want to subtract the last second value from the vector, and we don't know what is the length of the vector, then again we can integrate functions into functions, and now it's where it's getting interesting, right? We can use functions within functions and then get the desired result that we want. So let's create a variable called QUAX, and what we do here is my vec. Let's call my vec and minus. Okay, are my shadows getting stronger? Yeah, they are. Alright, it's fine. I'll edit it out. Okay, so QUX and then my vec and then minus. If you remember, I had created this variable called my vec length. So basically I'll call that, and then I'll subtract the last second value, which is this one. So QUX my vec minus, now if we just run QUX, you can see that the last second value here, my vec has the last second value as 3 is gone from QUX. Now I also want to show you this really interesting thing. You can create variables as indexes and then use that variable to extract certain values from a vector. So for example, we create something an object called indexes, which basically contains let's say random indexes like 4. Then we have something called let's say a repetition of numbers, let's say 2, and then it's repeated, let's say 5 times, yeah. And then we have 1 and 3 and 4, and then we also want let's say throw in a sequence there, 4 to 1. And now if I run this, we have an object called indexes. Now we can use this object, this variable, to extract whatever values are in this concatenation. So what we do is, let's take my vec again, for example. So my vec, yeah. So in my vec, what I do is square brackets and then type indexes. And you can see whatever the value of this concatenation is, I'll just type it out here. There we go. 4 2 2 2 2 1 3 4 4 3 2 1 are the indexes, and for these respective indexes, these are the value that has been extracted from my vecs. Is 4 3 3 3 3 3 5 2 4 4 2 3 5. Right. So that's basically almost everything about indexes, apart from this thing that you can also create concatenation of indexes, which can be used to subtract it. Let's say from my vec, you want to subtract the value, you want to subtract the value of the third and the fifth. You want to subtract the third and the fifth value from that my vector. If you just run that quickly, oh sorry, this should be again square brackets, my mistake. There we go, 534. I can see the third element from my vec, which is I'll just print it out, yeah, my vec. The third element from my vec, which is 2, is gone, and the fifth element, which is 5, is gone. You can see it's not here. It's not here. Another very exciting thing of knowing the index is that we can replace a certain value from a vector or many values from a vector with certain variables. Let's dive a bit complex directly, since you have all the base knowledge earlier. So we have some, let's say from my vec, from that vector my vec, what you want to do is take the indexes, let's say 2, 4 and 6. You take these and these indexes, these values, and then you want to assign it a different value altogether. For 2, 4 and 6 especially, nothing else is touched. It's just that the index 2, index 4 and index 6, whatever the value is 2, 3, 4 and 4, to be replaced with, let's say a value of 9 for that matter. So what you do is you just assign it like you assign a random object or a variable, and then you run it. And now if I type my vec again, if I run it, you can see that the second and the fourth and the sixth is replaced by 9. Now what if you want to replace it by different values? I have the same function, but I want to replace it by different values. So here a very important concept comes about something called vector oriented behavior of R, which basically means that R will try to match the number of values that is assigned to the number of values that is assigned to the number of values that is actually present. By this, what I mean is that, I'll just show you by example. If you want to replace 1, 2 and 3 for 2, 4 and 6 respectively, it will replace 1 for 2. That's the first index of this concatenation, not of the vector in general, of just this concatenation. I'll just show you. So you can see if I type my vec again, you can see now 1, 2 and 3, it replaces the first, second and third index with 1, 2 and 3. Now what if we just gave it 1 and 2? Now what will happen is something called recycling of indexes, which basically means that it will replace for the second index 1, first index 1, the second index 2, and the third index it will go back again till 1. So to show you an example, you can see it throws up a warning. It is not a multiple of the replacement length. That means it's not same in length that I'm trying to replace, so it will recycle it. Now if I just run this, you can see 5, 1 is replaced for the second position, 2 is replaced for the second position, and for the third position again 1 is recycled back. So if I had, let's say, put 8 here, yeah, what it will do is it will recycle again, and then you can see 1, 2, 1, 2. On the 8th position it's given 2. So it's very helpful to know that how R uses these values, because when we use arithmetic functions, when we do arithmetic functions or any sort of for loops in R, we need to be mindful of this vectorized behavior, of this recycling behavior. With that being said, we have actually come to the end of this video. If you have any doubts, please make sure to just put it in the comments. I will get back to each and every doubt, and in the next video we are going to talk about something called matrices and arrays, which are vectors which has 2 elements to it. It's like a 2D element, so it has its horizontal index, as well as a vertical index. We will delve deeper into that in the next video. Up until then, I hope this was helpful, and if it was, please make sure to subscribe. Thank you and have a nice day ahead.